In this video, I will introduce the method of analysis we will use moving forward for circuits with diodes. I'll do this with the same simple circuit, but before we do that, I want to preview where we're headed. Too often, determining what region a diode is operating in is left to your intuition. And intuition can certainly make your life easier and your analysis faster, but I want to give you the ability to support your conclusion of which region a diode is operating in. So look at this circuit and try to use your intuition to determine the region the diode is in. Let's develop a methodical approach to determining the region. I'll analyze this circuit directly in the next video. For now, with a single diode, we can treat the diode as the load and Thevenize the rest of the circuit. We would like to use the linear analysis methods we learned in our circuit analysis courses, if we can, but we are coping with the nonlinear VI curve of the diode. To bring the linear methods, namely nodal, back into play, we will make some linear assumptions, analyze the circuit using those assumptions, and then check those assumptions against the shape of the diode's VI curve. In each case, if we assume the voltage across the diode, we check the current through it. If we assume the current through the diode, we check the voltage across it. Let's treat each region in turn. We can see that this diode is forward biased, but let's do some analysis to defend that position. If we assume the diode is forward biased, we use an approximation of the voltage. You can start a good nerd fight amongst electrical engineers as to which voltage to assume, but generally something between 0.6 volts and 0.7 volts is acceptable for a silicon diode. Now for an admission. This plot is not to scale. Reality is closer to this. Since it's exponential, we ran out of screen. That's why we use a plot with a similar shape, but slightly different scale. Let's clean that up for now. The exponential shape of the forward region means that equal changes in voltage take larger and larger changes in current to happen. Let's keep track of the current as we take fixed steps of the voltage starting at the origin. The first steps have small currents on the order of picoamps and nanoamps. Some current starts to flow as we approach half a volt, and we finally get to a milliamp when there is 0.6 volts across the diode. In the step between 0.6 volts and 0.7 volts, the current rises by about 48% the rise the current saw from 0 volts to 0.6 volts, a much larger step. The exponential really takes off as we take the next step. Beyond that, we need a taller screen. The voltage tends to settle around the 0.6 volt to 0.7 volt assumption. This is generally adequate to get a good estimate of what the circuit is doing. We can justify this by varying R Thevenin in the circuit shown here using the nonlinear method from a few videos back. If we vary R Thevenin from 1 ohm to 1 mega ohm, we see the range of VD1 to be from 815 millivolts to 458 millivolts. So we pick something in the middle. I tend to use 0.7 volts, but 0.6 volts is acceptable too. Or 0.65 volts. These are all reasonable values for a silicon diode. I'll stick with 0.7 volts for now, but we'll mix it up in other videos. Let's use the 0.7 volt assumption in a linear system developed using nodal analysis. With only two unknown node voltages, I only need two equations to find them. As I usually do with nodal, I start with finding voltage sources and writing a KVL for each. I'll do that for the 5 volt supply. And in this case, since we've assumed a voltage across the diode, we treat it the same as the voltage supply, with the positive side of the voltage on node B and the negative side of the voltage on ground, we get this KVL. For this circuit, that is it. I don't even need to solve the linear system since I have the node voltages directly. That won't be the case with all circuits, so let's enjoy it while we can. But these node voltages are only valid if the assumption was correct. If the assumption is not correct, I have to throw them out and start again with a new assumption. Since we assumed the voltage across the diode, I will check the assumption by finding the current through the diode. If you're clever, you notice that the resistor is in series with the diode and you find the current through the resistor. If you're not clever, or the diode is not in series with any one resistor, you write a KCL on one side of the diode. I will write it at node B. Solve it for ID1, and use Ohm's law to rewrite the current in terms of the node voltages. Plugging in the values, we calculate the current. We now have the two values that define the operating point of the diode if this assumption is true. I usually just visualize the next part in my head, but let's get it on the screen. I think about the VI curve and think about where the operating point lies. Here we can see that the calculated value could feasibly be on the VI curve. This won't be the case if the assumption was bad. Let's consider the same circuit with a different assumption. In this case, let's assume it is reverse biased. Most of the time, it is okay to simply think of the current through the diode as 0 amps. We write the KVL for the 5-volt supply. Since we don't have an assumed voltage across the diode, we write the KCL at node B. We can rewrite the resistor current in the usual way. Previously, we used the nonlinear diode equation for the second term, but now we're assuming the value is 0. Now we have a linear system we can solve for the node voltages. Solving the system gives us a solution for the node voltages. We already know the assumption was incorrect, but let's take a look at how we confirm that. We assumed the current through the diode, so we check the voltage across the diode. Collecting the results of analysis for the operating point, and considering where that is on the VI curve, we see that it is not feasible to have positive 5 volts across the diode and not have current flowing through it. The point is nowhere near the VI curve and is therefore not a feasible solution. One more bad assumption to consider. This time, we assume the diode is in the breakdown region. Similar to the forward region, the nonlinear VI curve is exponential here. The specified breakdown voltage happens to be the voltage that the diode will settle at when in this region. A typical value may be specified as 75 volts. If we are being consistent about polarity and current direction labels, we are actually assuming the diode voltage is the negative of that value. The analysis is similar to the forward region, only with a different value for the diode voltage. And again, we assume the diode voltage, so we check the diode current. We now have the two parts of the operating point. And consider where it is on the VI curve. We can see that this operating point lies in the second quadrant, and is not a feasible solution. Therefore, the node voltages we found with this assumption are not valid. Now that we've made all three assumptions, let's organize the approach. In the forward region, we assume the diode voltage and check the diode current. If the diode current is positive, we're likely okay. I put an asterisk on this criteria because it is possible to have such a small current that we are not in the forward region. If that feels vague and ambiguous, good. It is. If the operating point is too close to the border between regions, the inaccuracy of the approximation prevents us from making a firm conclusion. When you get this feeling, stop and revert to using the nonlinear system of equations approach for more accurate results. In the reverse region, we assume the diode current is 0 amps, or that the diode is an open. We check the diode voltage. If the voltage lies between the breakdown voltage and the assumed forward voltage, the assumption is likely okay. Again, if it gets close to one of the region borders, revert to nonlinear analysis for more accurate results. In the breakdown region, we assume the diode voltage is the negative of the breakdown voltage. We check the diode current. If it is negative, the assumption is likely okay, subject to the same ambiguity as the other regions. Now I've applied all three of these assumptions and checks to a forward biased diode in a circuit. The first assumption succeeded, the subsequent two failed. I am going to follow this process on circuits with diodes operating in other regions, but let's move up the complexity scale. I'm going to leave the other cases to the next videos. Which region is this diode operating in? If you want to find out if your intuition is right, stay tuned and good luck.